Alright, so I am Shane Leaf,
And I'm Chris Dent.
and today we are going to show you a little bit about a wonderful process that we're going to try to optimize called beer fermentation.
This project highlights the most optimized method for a brewery system. We have assembled equations, mathematical models, charts plotting concentrations of the elements involved, and ultimately a Simulink model that shows this process in its entirety.
Alright, so I'm going to start this out with a little bit of a fun fact about beer, because everyone likes alcohol. Brewing alcohol is actually a very ancient process. In ancient times, it was considered healthy because it killed the bacteria in the really dirty water that they had. Now, as time goes on, processes and other things get developed and refined, such as fermentating and knowing that alcohol isn't good for you. And batch operation is now one of the primary methods in fermentation. This is nonlinear and conditions are changing with respect to time. There are also factors in fed batch and continuous systems. And in fact, none of these systems are on their own the most optimized way of brewing beer, but each provides some problems to address and a scope on how to solve them via nonlinear equations and matrices as discussed in the following. Okay, so fermentation is a natural process that creates different outputs every time that are close to each other but not exact. And so for that reason, we're not be able to create a model of the system that gives a definite output for every single time. So the goal in this is to create a model and a function that has a theoretical output that is close to what the output in real life is going to be. And there's a lot of different variables that come into play in fermentation, but the main one is temperature.
Like a standard distillation, not necessarily in the production of alcohol, acetate and similar organic byproducts are often a side result of this process. Distillation, for those who don't know, is the process of boiling a substance to the point that it vaporizes, and then allowing that vapor to cool until it becomes liquid again, and thus removing the acetate or whatever other compound from the original batch in this new distilled process. For brewing alcohols, however, some of these byproducts are welcome to a certain point, depending on the sought taste of the beer. For this reason, lagers are brewed quite differently, with more attention to removing diacetyl than an IPA is, for example. Besides diacetyl, we also really focus on ethyl acetate, which is safe to consume unlike regular acetate. And that's something that provides a much more fruity flavor, and it's even more popular in wines. Keeping in mind the effects of the brewery byproducts we just discussed, the equations below were developed to establish the desired amount of ethyl acetate and diacetyl, both with respect to time, in the end. These will be further noted in the full model in Simulink. Additionally, the equations to the right describe some of the variables within the equations for the byproducts, again with respect to time, that are used for establishing how much acetate and diacetyl we want in our system. Some of the other equations in there explain the fermentation inhibitor factor, the specific rate of latent fermentation, substrate consumption rate, and specific yeast growth rate. All of these are factors that are important to the overall brewing process.
Alright, so the figure on the right shows the fermentation process is in the form of a diagram. It can be really broken down into two phases once the yeast is introduced to the wort, which is what becomes the alcohol. And the first phase is called the lag phase. And the lag phase begins once the yeast is introduced. There are three types of cells throughout this entire process. They're called lag cells, active cells, and dead cells. So once the activation begins, that's the start of the lag phase. And there's no fermentation occurring at this point. So all that's happening during the lag phase is the dead cells are settling to the bottom of the batch, while the lag cells are being transformed into active cells. And the fermentation doesn't begin until 80% of the lag cells are transformed into the active cells. So once the fermentation phase begins, there are two more processes that begin happening: fermentation, and redundantly, and growth. And these are both still occurring while settling and the transformation are already happening.
For isothermal batch fermentation, this is a diagram that shows a way of trying 5 different constant temperatures in the fermentation process. The 5 temperatures used under this model were of 8, 12, 16, 20, and 24 degrees Celsius. Each of these was repeated 3 times for the most accurate numbers available, and were read for the best times and temperatures in regard to the byproducts and the sugar concentrations.
The figure on the right shows mathematically defined functions of time of an optimized system displayed against experimental results. The variables that were observed are shown in the slide to the left. This was done for a constant temperature of 12 degrees Celsius. As you can see, the experimental results lie very close to the defined lines. This experiment was also done for constant temperatures of 8 degrees Celsius, 16 degrees Celsius, 20 degrees Celsius, and 24 degrees Celsius. All of these experiments resulted in similar results. So at this point, using these graphs, you're able to pick the point where the temperature needs to change in the fermentation process, or the fermentation process is stopped altogether.
This, the Simulink model developed in the European Control Conference by Carrillo-Ureta, Roberts, and Becerra, is the best optimization of a fermenting system. This Simulink model breaks down the various factors that go into the process of brewing beer and optimizes them for the best possible end product. The temperature and yeast are the first function considered, after selection of wort and hops in regard to taste. This returns new functions with respect to the ethyl acetate and diacetyl concentrations, which are then considered with regard to the input goals and to the biomass quantities summed in the previous equations, as noted as X lag, X active, and X dead, through the demux. Time and temperature are the most important variables in this simulation. They are the variables that will dictate the ultimate concentration of sugars and the byproducts. There are a number of methods to brewing beer, with many impressive distinctions. This is a model that represents one that can retain the most of any concentration, such that the goals of the final product have the most options available. In conclusion, we'd like to compare this model to a similar model used in the distillation process of alcohols such as rum, gin, and moonshine, as well as simpler fermentation processes, such as in the making of wine.
And if we were to do this project similar to this again, we'd like to find our own experimental data and get more ideas to the many contributing factors of this elaborate process.
We welcome questions about our presentation to be sent to CPD 5115 and SPL 5183. Please just send your question to both of our emails so that we can get back to you as fast as possible. Additionally, these are the references we used throughout our presentation. The Simulink model by Carrillo-Ureta and others was the one we learned from the most in the modeling of what was an optimized process can be.
That's all, folks!